so I expect the class to be a bit late. But anyway, we will start in about 5 minutes time. Are you all able to view the files uploaded in Moodle? Right? So lecture 1 has been uploaded. I just uploaded lecture 2. For these 2 lectures, don't worry too much, but just be aware of the things which I tell you. 3, 4, 5 are the more mathematics intensive ones. So I will do a bit more of tutorial or practice questions for those kind of lectures. I heard from Professor Alfred that you thought that robotics was over, is it? No, he taught you more of the sensor actuators. I will touch more on the robotics fundamentals. Right? Okay, we shall start our lecture soon. Very good morning to all. Very good morning to all. Okay, let's have a bit more energy as we go on to the whole lecture. My name is Professor Mustafa. I'm with the SIT faculty, not with the Glasgow faculty. Just like Professor Alfred, right? And Professor Fannin, which is from Glasgow. So I will be covering the second half of the robotics, the R4N module. Now I will cover robotic fundamentals. We will talk about when you have a robot configuration, or a robot structure, how do you identify this robot structure? What is it made of? Right? How do you determine its model? Now why is the model important? Because you will want the robot to do something. You need to put in some inputs, or you tell it that I need to reach certain targets. How do I get the model of the robot with the particular so-called requirements or task requirements, customer requirements that you have, right? That is more kinematics. So you look at inputs that you have, what are the outputs that you get, and and vice versa. You have certain output, what is the input that you need for the robot. It's good to know all these fundamentals because when you, let's say when you go on to the industry, you are working with robots. You will not deal with these models anymore. No? You will have like a pitch pendant or the interface. You just key in the inputs, the robot controller will do everything. Right? So why are we going to do this? Why are we learning this? Right? When everything is there. The reason why you're learning this is that when something goes wrong, you as an engineer know what to do. Because you understand what's working behind the software. It's not just a black box to you. Right? So having that appreciation, understanding will help you to become a better engineer to troubleshoot. You don't have to rely on these robotic manufacturers to hold them down. Maybe a day you will take 500 to 1,000. This money will transfer up to your boss, and this transfers to cost. Right? And your boss will say, hey, you learned robotics before, right? Troubleshoot. Right? So that's why we are having kinematics. How do you model the robot? And you understand what's going on. Now, I will cover lectures 1 to 5. Lectures 1 to 5 doesn't mean it's week, what's week now? Week 5, right? 6, right? Doesn't mean it's 6, 7, 8, 9. I will go on a bit earlier, faster a bit for lectures 1 and 2, right? Lectures 3, 4, 5 are the more of the fundamental mathematics. So I may spend a bit more time. I will do a lot of practice questions with you guys, so you can appreciate what is being taught. Okay, before we start, I'd like to just play a quick video on robotics, so we have a quick overview. And as we go along, these 2 lectures, I may cover lecture 2 today as well. But don't worry if you don't have a notes, it's not critical. Just take down the key points. But in these 2 lectures, there will be quite a number of videos. Why I would like to play videos, I want to show you what's being there in the industry. A big background about myself, I was from the industry for the past 10 years. I joined SIT about a year plus. Right, so I was doing a lot of industrial projects involving robotics, mobile development, robotic R&D. So that's why my lectures will be very tuned towards what is very industrial oriented, industrial application kind of lecture. So I will have that kind of about perception when I talk to you guys. Okay, let's move section.
Thank you. And the robots are not. You'd think the robot revolution would have happened by now, with the software robots taking over the world, becoming our overlords, making us work in the tungsten mines. Well, the thing is, the robot revolution already is happening. It's been happening for decades. It's just been a lot less bloody than the movies made us think it would be. And the robots are not self-aware yet, but in all likelihood, your car was made by a robot. These days, there are robots helping spacecraft dock at the International Space Station, and you might even have one faithfully vacuuming your kitchen floor. Not exactly Skynet, but all of the convenience that we already enjoy thanks to robots took decades of hard work by scientists, and some of the problems that robotics engineers were struggling with 50 years ago still haven't been solved. So there's a whole lot of history that went into the robots that we rely on today, and it just might help you understand why we don't have robots taking care of our every need or forcing us to mine their tungsten. If we're going to talk about the history of robotics, first we need to talk about what a robot actually is. And for such a common term, it's surprisingly slippery to define, but technically speaking, a robot is just a machine designed to accomplish a task. That's it. Now, it might sound like that would cover everything from a 4-function calculator to NASA's Pleiades supercomputer, but that is not what we're talking about here. When we talk about robots, we're really talking about machines that use their programming to make decisions. For example, if you, a human, decide to pick up a coin from in the ground, there are three main steps you have to go through. First, your eyes need to see the coin, and then send that information to your brain. Then, your brain processes that input and uses things like previous experience to make a decision to pick it up. Eventually, your brain sends messages to your body to grasp the coin. Robots go through a similar process, but without getting Slim Jim at the gas station. They can go through that process because most of the time they have the components that let them carry out each step. They have sensors for input, control systems for decision making, and end effectors for output. Sounds simple enough, but developing each of these components can be challenging. Sensors have to be able to detect things like images and sound accurately. Effectors have to be flexible and fast enough to do what we need them to do. And the control system has to make all of the decisions necessary to get the sensors and effectors working together. Of course, there are so many different kinds of robots that these components can vary considerably, but that's the basics of robot anatomy. Now, if we try to talk about every advance that's been made in every subfield of robotics in just the past half century, we'd be here all day. But to understand how we've gotten this far and why robots haven't taken over the world yet, we first have to talk about how the development of industrial, humanoid, and military robots got the field where it is today. Industry is a good place to start because that's where robots first became useful. Since factory work can be repetitive and often involves lifting lots of heavy stuff, it's a perfect fit for a machine. The world's first ever industrial robot, Unimate, was installed on a General Motors production line in New Jersey in 1961. Weighing in at nearly a metric ton, it was basically a giant robot arm. Its instructions programmed on a huge magnetic drum told the arm to stack and weld hot pieces of metal over and over again. Soon, other car companies got in on the game installing their own robotic arms, but this first generation of robots was still in its awkward stage. The arms weren't particularly flexible, they were often powered by clunky hydraulics, and they were ultimately difficult to program. So when a robotic arm called IRB-6 came along in 1974, it was a pretty big deal. This was the first electric industrial robot that was controlled by a microcomputer. It had 16 kilobytes of RAM, it was programmable, and it could display 4 whole digits with its LEDs. Developed by Swedish engineering firm ABB, this robot was used to perform inauspicious tasks like polishing steel tubes, but it was a crucial step toward developing robots that were easier to program. But while controlling robotic arms was getting simpler, another issue came up. You can give a robot as much programming as you want, but if it can't see, it's not going to be able to do even seemingly simple things like figure out which box should go where on a pallet. Crude visual scanners had been around since the 50s. They could only see black and white, and the resolution was worse than what you get from a flip phone camera. But to give vision to industrial robots, engineers had to tap into another field that would completely change the robotics game: artificial intelligence. Now, artificial intelligence, or AI, is another broad, vague term used to describe any attempt to make a computer do something that we'd normally associate with human intelligence, like translate languages or play chess or recognize objects. In the 60s, the problem was that even though AIs were getting better at complex reasoning tasks, like playing chess and proving mathematical theorems, it was incredibly difficult to actually get the programs to interact with the real world. There's a difference, for example, between figuring out the ideal placement of wooden blocks in a theoretical model and actually moving those blocks into place. Because moving them involves a whole series of discrete decisions and actions, and the robots at the time simply couldn't manage that. The robot's vision isn't just about taking pictures, it's also about recognizing objects so that they can react to things in situations in real time. By the late 1970s, engineers had developed new algorithms that allowed cameras to recognize edges and shapes by using visual cues like highlights and shadows, but these programs were still just experimental, stuck in research labs. That all changed in 1981 when the first industrial robot got the gift of vision. A General Motors factory was once again the guinea pig, implementing a system called ConSight, in which 3 separate robots could use visual sensors to pick out and sort 6 different kinds of auto parts as 1,400 parts per hour moved by on a conveyor belt. Progress. For the next 2 decades, technology kept improving. Industrial robots were able to see better, move faster, carry heavier loads, and handle more decisions. These days, industrial robots are advanced enough that it's totally normal for a factory to install a robotic assembly line that handles nearly all of its production. And some industrial robots are heading in the direction of a more general purpose use, like Baxter, the humanoid industrial robot. Humanoid? Yet again, a very subjective term, but it just means human-like. For robots, that usually implies that they're designed to look and act as human-like as possible. So Baxter, for instance, is nearly 2 meters tall, weighs 136 kilograms, and has a screen for a face. It also has a vaguely human-shaped torso, 2 arms. But more importantly, it can be quickly programmed to do practically anything. If a factory worker or researcher has a task to do, Baxter can probably handle it as long as it's lifting less than 2.2 kilograms because its arms are not industrial strength. But it does need to be told what to do. If you want Baxter to stack some products in a box, for instance, you've got to program it by manually making it do what you want the first time, and then it'll imitate that task. And its shape may be loosely based on a human, but Baxter cannot walk or climb stairs or talk. So getting a robot to act like a human has proved to be a whole other ballgame, and it's one that researchers have been working on for decades. It's been slow going. The Wabot 1 is usually considered to be the first full-scale humanoid robot. Developed by researchers at Waseda University in Japan in 1973, it had arms, legs, and a vision system. It could walk, it could pick things up with its hands, and even talk, except that it could only reply with pre-recorded responses to very specific statements, and it took 45 seconds to take one step. This bot and its successor Wabot 2 were a really big deal in their day, but they also pointed out an important fact. It's just much easier to design robots to do one task at a time. So recently the thinking has been, if general-purpose humanoid robotics are out of our grasp, we might as well focus on making something that can do at least one useful task. That's why in the past 10 years there have been more household robots in use than ever, programmed to perform a single function, like vacuuming the floor, mowing the lawn, washing windows, or cleaning the pool. They're not quite rosy from the Jetsons, but they were all made possible by the advances that came before them, like having the ability to sense their surroundings and make decisions in order to navigate the world. And it's not like researchers have given up on the humanoid front. There are humanoid robots in development that can perform some impressive feats. Honda's Asimo, for example, can walk at speeds of almost 6 kilometers an hour, climb up and down stairs, carry a tray, push a cart, among other things. So again, progress. You just can't buy one. For the time being, Asimo is basically a research tool and a spokesmodel for what the future of robotics might look like. And probably the most cutting-edge research going on in robotics today is being done by the military. Take Bear, a military robot that's been in development since 2005. Unlike with humanoid or even single-task robots, in the military, robot design is more about function than form. So Bear has some humanoid components like a head and 2 arms, but instead of walking like a human, its legs are covered in treads like a tank. The legs have a joint that acts kind of like a knee that can rotate all the way around. Using their special limb design, Bear has proven really good at moving through rough terrain, including stairs. It can climb through debris and carry an injured soldier back to base. It can carry light loads, tell it to go to a location, and it'll go there. That's a lot more than most civilian robots can do. But discussion of military robots would not be complete without talking about DARPA. A division of the U.S. Department of Defense, DARPA has been working for the last 50 years to turn even the wackiest of concepts into working technology, and it's been one of the most active promoters in the field of robotics. DARPA has stoked innovation by holding robot competitions, held contests for autonomous vehicles where robotic cars compete in a race hundreds of kilometers through the Mojave Desert. And in the summer of 2015, 11 teams will compete in the DARPA Robotics Challenge Finals, where human-supervised robots will try to carry out complicated and kind of dangerous tasks associated with disaster response, like scrambling over debris and carrying things to safety. The aim is to develop robots that can be sent into dicey situations without putting human lives at risk. And we're getting there. So robot tech has come a long way since that first robotic arm in 1961. It's just that, as often is the case when it comes to humans and technology, we can dream up awesome designs and uses for robots faster than we can actually invent them. For now, I'm perfectly happy to have a clean kitchen floor and my freedom from the tungsten mines while science takes robotics to the next level. Thanks for watching this SciShow Infusion. If you have questions or comments, be sure to let us know on Facebook, Twitter, Tumblr, or down below in the comments. And don't forget to go to youtube.com/SciShow and subscribe.
Okay, this was just a brief so-called preview of what's the history of robotics like. This is a very recent video. I like to start off our robotics lectures with this quick update of what's going on, so everybody has a better awareness of what is robotics, what do they entail. You all learn about sensors, actuators, how they come in place when you actually see a robot. Right? In terms of robot forms, there are so many forms that you can have. You have the humanoid type, you have just the arm, you have mobile bases, right? So robots are very, very specific in their task. You can say they are very dumb machines. To put it honestly, compared to humans. Right? We are so versatile, we can do so many things. But when you build a robot, it's specific for a specific task. The structure that you have, the end effector, or the way it manipulates things, or it does, is very specific, right? You can say industrial robots are a bit more generic, they can do a few other stuff. Okay. Okay. Now the first so I want to share with you the learning objectives of this particular series of lectures that you're going to have now. Right? First of all, I want you guys to appreciate this robotics technology that you will have and its impact on society. You have to be very aware. It's not so straightforward to just put in a robot. There are a lot of safety. If it's going to work alongside humans, a lot of safety issues to worry. Right? It's not about just put a robot in, okay, work together. No, there are a lot of things. Even if you want to bring a robot into your home, would you be comfortable? Let me ask you this. Would you be comfortable having a robot in your home? So do this, do that? Yes or no? How many of you all prefer? Just raise your hand. What? That means the rest what? No. If everything works, I also want it. Right? But what if the robot go haywire? Okay lah, you see the Roomba, okay, no problem, haywire, it just block your feet. But then even then it can cause you injury. If you have bigger robots that can serve you stuff, like they go haywire, they have to whack somebody then. Right? So you have to think about the implications. We still have not reached a stage where we are comfortable having robots in our homes. In hospitals, there's this slowly doing it. You go to KK, they are delivering meals to the wards. Even then, the robots will go so slowly. Then, if you happen to see this kind of mobile robots, what would you guys do usually? Go nearer, try to block its path. Right, that's what you're trying to do, right? It's human nature. It's like, hey, it's so interesting, let's catch up with it. Then that's where you need to have additional safety factors. That's why the robot will move very slowly so that it gets stopped in time. Okay? Again, as I was mentioning to the class earlier, now this series of lectures will enable you to develop the model of a robot that you will see. Now, why is this model important? You want to control the robot, right? You're going to give it some inputs, it's supposed to do something, right? So, what is the mathematics behind that? I will go through a quick overview of how you go about getting a particular model, mathematics model. Okay. Now, these are the topics which I will cover. Okay, today is just introduction. I will also cover a bit about industrial robotics, like lecture 1, lecture 2. So if you have not printed, don't worry so much. Lecture 3, 4, 5 is the one I want you to be very worried. It's mathematics intensive, and this is what's mostly going to be tested. Right? So I'm going to spend a bit more time on these lectures. I'll go through some practice questions. Now, when I say practice questions, doesn't mean they'll come out in exams, because I don't set the exam paper. It's the class both side. Right? But I want to make sure that you guys have a good understanding of the fundamentals, have a bit of practice, so when it comes to an exam, it's familiar to you to answer. Right? I also have a co-lecturer, Mr. Tan Lai Ming. He will cover from lecture 6 to 10, 11, sorry. Right, he will talk about more of Jacobian matrices. Jacobian is, okay, when you want to control a robot or control something, you will first start off with the position, right? Okay, I want to go here. Do this, right? When you differentiate position, you get velocity, right? So, if you look at velocity, when you are doing something, let's say I'm moving my acceleration across the room, this way, right? Now, position-wise, yes, I say that okay, from this point, you break down the path. Now, I want it to be fast, I want it to be slow. This is where my velocity comes in. right? But this is my so-called my task space velocity. I'll talk to you about task space and joint space in a while. So task space is your physical space that you want to do something. Now joint space is you need to move this joint, because if you look at the industrial robot, there will be actuators at the joint. You need to move the joints in a synchronized manner so that they give you that output that you need. Right? If you want a particular velocity at the task space, you need a particular velocity at the joint space. Right? So that is what this differential kinematics Jacobian matrix will help you to determine. So it's from your position. When you look at a model, you will get all the position equations. From there, you differentiate that, you get a Jacobian matrix. There's an easier way to use Jacobian matrices. So this is what will be covered in the second half. And you will also cover dynamic and a bit overview of. Okay, take note. These are all the dates that we have. Tentatively, there is one date on 4th of March. Okay, we will start at 10. Okay, just take note, 10 11. Right. These are the dates, these are the values. Now for Mr. Tang Lai Ming, there is one on 25th March, it's a public holiday. I will let him update you guys what that whatever. If he wants to dig it bigger or it's up to him. I leave it up. Alright. There is a date missing on 2nd of March. You all are aware of this career nexus, right? Career fair by SIT. So they are holding it on that date on the morning. So we will not have lessons on that date. But because of that, I will cover up in these few lectures. Right? So we don't have any makeup. Okay. This is a recommended textbook. For those of you all who are keen to pursue robotics later on, I would suggest you to get one of these robotics sets. Right? You can get it as a I'm not selling this company's book. This is not the only book. Just that the Glasgow site has selected this book as a recommended text. Still fine. You can proceed to buy a book if you are really keen in pursuing robotics later on. I believe you can find it in the library as well as in SIT. But if you need to borrow. Okay. There is lab work, right? You all are aware? You all will be using Lego Mindstorm. Again, Mr. Tang Lai Ming, he will be the one who will be conducting the labs. And I will leave it up to him to give you the updates on what exactly it is. But in the past few years, we have been doing robot wars. Basically, what that is we give you a set of Lego Mindstorm kits, right? With actuators, limit switches, controller, right? You form up either vehicles using regular wheels, tracks, so on and so forth, and you will basically form teams, basically, first of all, build the robots and fight against them. Okay? But one thing I want to share with you something. For the past few years, it's not the winner of the competition that has the highest grade. Okay? The reason why, sometimes it depends a lot on luck. Maybe that day you sway, you plan everything properly, but that day something jammed, then you lost out. But you know that your robot is very fantastic. So we are aware of this kind of things. So we will also look at how you build or you strategize to build your robot to fight the robot wars. Right? You have your presentation in the report. So these are the other things which we will also take into consideration. So competition is just a part of your assessment that contributes to assessment grade. What we are looking at more is what kind of innovative solutions that you can come out with to do the battle. Okay, whether you want to shoot the opponent into some kind of motion, I will leave it up to you. Okay, so don't be too focused on just creating a very simple model that can push it down. Yeah, you will win the competition, but when we evaluate your report, when you go through your presentations, we will drill you on what's the strategy that you want to use. Right? If your strategy is just to bash through, then you may not score much. Right? Okay, so think about this. You can check with your seniors as well what they did. Try not to copy their ideas wholesale, but some of them have very interesting concepts. You may improve upon the concept. Okay. Classroom rules, I only got one rule. Respect yourself and others around you. What does that mean? You all are here on how do you all finance your studies here? Self-sponsored, Papa Mama scholarship. Maybe some of you have scholarships. But what's the key thing that you all are here for? To have an increase in knowledge, get a degree, to have a better future, right? So let's be kind to yourself and to your friends. I mean, you are here, we have a dedicated time for you to do your lectures, just pay attention, try to come on time. I know today is rainy weather, so it's okay, no issues. Come on time, pay attention, if you have questions, you can ask me to come. Okay? I want to have a two-way kind of interaction with my classes. Any questions you can discuss. Okay, after class, it's also fine. Right? If you need to make phone calls, whatever, please proceed, go out and make a phone call. Right? Don't distract, no? That's all I ask from you. Right? Because this is your time to learn. Okay. Enough about that. Let's go on to lecture 1. Okay. For those of you who came in a bit later, we started off with a video, a brief history into robotics. Right? I just wanted everybody to have a feel of what's going on in robotics and an idea. Because this word has been flying around so much that people are, what actually is a robot? When they see a robot, they don't even know that it's a robot. Okay? So I hope that through these 2 lectures you will be very aware and you know what actually is a robot. There will be a background of robotics. I'll tell you how we classify robots through the way we control. Right? Is it a simple let's say a human user controlling it, remote control, or you have a bit of intelligence in the robot to make it do some decision-making capabilities, or is it very advanced that it can do multiple decisions? Right? So these are things which I will go through as well. Types of robots, very important. We look at the structures, the joints, what are the things that makes into a robot, and the components in the robot. Okay. The word robotics basically came out from this so-called a play back in 1921. This Czech writer, Karel Kapek, he actually kind of created a play which involves a robot. Right? Somebody created a robot. So in his play, this robot was basically like a robotic maid, just helping, like a robotic butler. Somebody in the home, and somehow the story evolves to this robot or this group of robots trying to take over humanity. Now this was something what he kind of came out as a player, right? And through that, actually that sparks the ideas in people's minds. There is a way we can use these sensors, actuators, put them together, and get these things to do useful things for us. Now you may have you have realized that there will be a lot of tools that you have in your everyday life. Let's say a hammer, spanner, wrench. These are all tools that you can use to make your work done better, right? But these are very passive. You are the one who are providing the actuation input. But robots is a bit different. You put in so-called actuators to the joint. You control the motor, that will control the entire structure to do something. Right? So it's becoming like an active system. Not very passive, not you control it but through electronically. Again, when we look at the history of robots, of course we know Transformers are this. I think everybody knows about Transformers, but have you heard about this? The thing called short circuit? Right? Maybe a handful of you may have seen it. But that was one of the first movies which I saw, which at that time I didn't realize it was a robot. But I said, wow, this is quite cool. Can do this, can interact with humans. But you never think of it as a robot. Right? Again, Star Wars. Right? Star Wars also was one of the first few movies that introduced robots. Robocop, how many of you are familiar with Robocop? Before the new Robocop movie came out, there was a old series. Right? So a lot of some of the movies are also remakes. Right? Of course, the new ones are much more cooler. Black color. Terminator, this one is typical. I think most of you should have watched it. Right? Again, AI. This movie is slightly different from the rest. The rest of these movies is just an action pack, Okay, fight a war, do this, do that, do something. But AI is to challenge the audience who is watching. To see that, hey, if I really have a robot who is with me, who's doing things with me, do I get some form of affection or do I build a relationship with that robot? It kind of it's a different kind of message that it's sending on across. It's not just a no-brainer kind of just sit there and watch. It kind of wants you to think a bit. If you have this kind of things with you, this kind of robots, do you just treat it as a piece of machine like a car? Okay, I'll use the thing, okay, go. Or is it something more? Okay. Again, iRobot is still a bit more of action pack. Not much. AI is the one. Okay. Real still again action pack. Right. Just saying that as we evolve the AIs. Now AI, okay, the basic form of AI is AI input. Right. You have certain inputs coming in, certain disturbances, how the system reacts to it. When we go to higher level, we have systems which looks at different kind of scenarios and make some intelligent decisions moving forward. Okay, so it's slightly different, right? When you go to AI, there's a lot of things that still have not been done. It's still in a very infancy stage. Yes, we have developed neural network, fuzzy logic controllers, so on and so forth, but nothing has beaten the human mind's capabilities of taking decisions yet. Okay? But of course, we won't touch so much of this in this course. Right? This runs as module by itself. Okay. How many of you have read Isaac Asimov? Anybody? Yeah, if you got time later, maybe not today but if you have time, try to read some of it. Isaac Asimov. This was one of those books which makes you think, hey, if robot is kind of with us in society, what are the implications, what can happen, so on and so forth. But in this book, right, he kind of said that there are 3 laws of robotics, which he always keep so-called promoting in this book when you read the book. First one is a robot may not injure a human being or through inaction allow a human being come to harm. Wow, so easy to say, But when you think like, if I need to program this, is it so straightforward? What is don't let do not allow a human being to come to harm? If I ask you all to tell me, okay, spend you as a research project, come up with a program to ensure that a system will never harm a human being. I don't know how long you will take. I don't know how long I will take. Why? Because there are so many scenarios which we can go through. What is harm to a human? Right? How are you able to look at all the scenarios, the infinite scenarios available, and create rules to cover this? Very, very difficult. Right? So, although this is a writer, very philosophical, must not let the human come to harm. But in reality, when you put it down to technical nitty-gritty details, it's not so straightforward. Okay? So bear in mind. Second one is a robot must obey orders given by human beings unless it conflicts with the first law. That means, okay, you can say that the robot is your slave. You got multiple users, then now maybe you want him to do something, you want him to do something. Who should I listen to first? Right? When you start thinking about these laws, a lot of things, you can start to ponder and see, hey, will this really work? what are the things I need to do to make this laws really work. Again, robot must protect itself from harm. Now you must ask the robot to protect itself. First, don't let human being come to harm. Second one, follow orders from human. Third one is protect itself from being harmed. And what if it's can put it in a way, if a human is being harmed and it is being harmed, how is it going to decide it? Like, unless you say that I keep priority, then the robot just sacrifice itself. Sacrifice itself. Then came this number 4, which he called the zero norm. It may not harm humanity. Even bigger. Not talk about human or humanity or society. Okay, so but these are all very philosophical things. But let's come back down to the ground. Okay, there's this Professor Gerard from Oregon Institute of Technology. Okay, I like his quote because it's very real. A robot may take a human's job, but it must not leave that person's jobless. Right? You all may have noticed the past 2-3 years, government have been emphasizing on productivity. How do you do productivity? Is automation the way to go? How many of you think, okay, by being productive, automation is the way to go? Can you raise your hand? Okay, partially, not fully. Okay, how about partially? And the rest, I presume you want robots to be involved in your work. Okay, what's the take is, yes, those who answered partially, they are the more or less, this is the way we should go. But before doing partial automation, we should aim for mechanization. So what is mechanization? Mechanization is the one step before automation, where automation is you put in active systems. Mechanization is basically things like, hey, if I see a person doing very manual work, okay, maybe he's bolting the nut by himself manually. Maybe you can just get a hand drill, those nut wrench. These are things which called mechanization. Right? We go with that step first. So we do step by step. We never go into automation one shot. Okay, you do it bitwise, optimize the whole process, see if it works, then you again implement another set of automation procedures, optimize it again. Because when you put in an automation system or semi-automated system, it's not like instantly what the thing will work. When you all become engineers, when you all meet with these kind of bosses, educate them. Tell them it's so easy to do that. Okay? It takes a lot of time. So that's what you see. That's the one of the reasons why automation has not been picking up yet. The mindset is wrong. They think that I want to do automation. By next month I must get the thing set up. Cannot be. It takes a while. Sometimes it takes years, because you're trying to automate. As you mentioned, as I have shared before, a robot is doing a very specific task. And it goes a whole process with so many different tasks, and you want a few machines to handle everything. And you want the same output, even better, maybe 50% more. Okay, so when you go and do all this kinematics modeling and everything, all the other topics, I think you realize, hey, there's a lot of things involved behind this, rather than just straight away automate, right? So I want to plant this awareness in you guys. Even though that you all, maybe you all as engineers go out and work, say, hey, let's automate this thing, what you're asking for. Okay. You can automate, but make sure that you are also capable to take care of the automation system. Don't be relying on manufacturers. Once you are relying on them, that's it. They will hold you ransom. Anything, okay, can you come down? Yeah, sure, I'll charge you maybe 500 to 1,000, maybe even more. Then they'll take the time maybe one whole day. Then you see from when sekali actually within a few minutes you can solve it. Because you understood the concept. Okay, a lot of things are like that. They are not as complicated as you think it is. Just that you never understood it yet. Then you call this specialized. Unless it's very specialized machine, very complex. Okay, that's fine. Right? By simple things that you can adjust here and there, maybe just to adjust the TIE gain of a particular setup, then you will have a more smooth flow. Okay. So again, these are the things I want you to be aware. Again, okay, this is what workers or engineers, for example, most of you will never raise your hands up, will be thinking, right, robot is taking over your job. Actually, it's not true. Okay, robots are there as tools. They are not there to take over your job. Okay, I need to also dispel this fear that you may have. Right? If you use them wisely, by all means, they will be a good companion. They will make you into a more productive employee. Right? But then you have to upgrade your technical skill sets to be able to handle the machine. Anything happens with the machine, you know how to do it. Okay? So don't think that robots are going to take over. No, actually you need to do different. It's just that we have to stop thinking as an unthinking engineer to a thinking engineer. Right? Okay. Okay, this is just to share with you what automation can do to your productivity. Okay. Now there are a lot of scenarios where it's very hazardous for a human to actually be carrying out this kind of stuff. For example, if you need to paint this kind of aircraft, there's a lot of inaccessible areas. Maybe the outer ones is fine, but the inner ones, hey, why not use robots to help you increase your productivity? Right? While you paint outside, the robot is doing some of the work inside. Right? You use robots to complement your skill sets. Right? Another thing for think. Okay, if you look at this picture, this is one of the aerospace components. So aerospace, they are very precise. Right? From the fact that it comes up from the milling machine, right? When you build something, if you look at the edges, they are all burrs, they are not smooth. There will be some pieces that are turning out. These people have to manually go through all the edges. Can you imagine that this is one part? Can you imagine how many edges there are? You have to do this day in and day out. Same or not? Or happily okay? 5K also you want to do it? Sure or not? How long can you last? Then you say you can go find something else to do. Right? So fatigue will set in, no matter what, okay, maybe you enthusiastic, okay, for one whole year, you on. Okay, that's me. Don't say one whole year, maybe in a week also. Monday on, Tuesday on, Wednesday on, okay, Thursday okay, Friday on, weekend coming in. Then your accuracy will go down. So these two are linked. Okay? Hazardous environments. So let's say you are working in nuclear power plant, you do inspection of those nuclear cells and all this stuff. Who will want to do this? I pay you 10,000 euros. What do you do? Right? So that's where robots come in. Right? Now repetitive tasks is also linked to this kind of things. You're doing same thing over and over again. Government policies, this is something you need to be aware of. It depends. Let's say for developing countries, because labor is cheap, they do not have the urge or the need to go high tech. So even governments will not bother. But you realize what's happening in Singapore? We used to be low tech, but government realized that if we don't go up that value chain, we will lose out. We will lose out to our neighboring countries who can do the job as well as our banks. So we have to be one step ahead. Right? You look at China, you think they are low tech, I tell you they are even more high tech than us. They got the whole mess. Just imagine, look at the population. Even they are 1% compared to our 1%, you look at the amount of natural numbers. They can easily do a lot more things, and they are doing a lot more things than us. Right? They can pick up. We started early, we reached there, they are like exponential. They just get 1% of the population to think. Right? So these are all very critical factors. You need to understand what's happening and affecting you as engineers. Okay. Again, you have this amount of workforce, you have this amount of profit. And if you complement it with robots, right? Can you tell me in the short term, if I just started implementing robots, what will happen to my profits? Drop. Right? Why? Yeah, because we bought these machines. Right? It's okay, just to share with you, this kind of, let's say, robotic arm, say 60 kg payload, can cost you about 60k. 50 to 60k. And this 50 to 60k is just pure position control. We also have force control type of robots. Robots can sense force about 100k. That is where you will need these robots for this kind of task when you're doing delivery, where you need to have a sense of touch. Because everything is not the burst or whatever these things are, they're not regular patterns, they are random. So one way to go about it is instead of positioning, it's just force. So you feel the force and then you adjust your delivering approach. Okay? Again, yes, productivity increase, profit increase, but this is over the long run. Please take note. It's not if you look at this profit, maybe this one in a year's time you can have this profit. But this one, maybe after a few years, then you start getting this kind of profit. Once you have your return on investments from your investments to your automation devices. Alright? So bear in mind, this is looking at the economics and finance point of view. I'm not going too detailed, but I want to be aware. Okay? So what are the undesirable effects of introducing automation? Okay, put aside your robot taking over a job. Okay, what are the undesirable effects in your workplace? Can you spend a few minutes and think about it? Remember, it's about your factory floor, your working environment. What's the undesirable effect? Okay? Okay? But in terms of undesirable effects, so when something goes wrong, make sure you stop the robot from doing its work, right? Once you stop, your whole line is stopped. Your downtime will decrease. But if you have, if you rely on, let's say, manufacturers, these suppliers, you have to wait, call them, hey, my robot is down, it's not down. Solve it, your downtime increases. What's the one way of overcome or minimize it? Okay, prepare yourself. Now I will have my opinion, this is just my opinion. That is a good answer, prepare yourself, right? But you would want to make sure that you are familiar with your equipment. So basic maintenance, you can do. Okay, basic repair you can do enough. The other thing is, because you're aware of this so-called your component that you have, you can do your own maintenance. Now when you, this is another thing that we will not be talking about, but it's something I want you guys to be aware of. Right? Maintenance policies, these are very critical. Right? Just like your car, right? You have a car, you bring it to servicing. You can go bring to servicing, yeah, no problem. 3 years, 4 years, just down, whack. Then later one day a car cannot start. But if you regularly go, say 6 months, 1 year, you prolong your life of your equipment. So take note of that. Alright? But yes, that's a good point. If you are aware of your equipment, basic things you can do. You can troubleshoot yourself. There's something else which is a bit more complex. Right? But I'm not saying that every time will be basic problems. Sometimes it can be major problems. Right? But this is one of the undesirable effects. If it's human workers, more or less, hey guys, maybe for one department, can you guys come in and just help out? Right? So things you need to take note of. What else? That's the point, yeah.
Intermittent problem when parts start to break down, very hard to debug or recognize.
Right, correct. Now this is because if your process is still being optimized, right? In the process of being optimized, you will encounter a few of these bugs here and there in the initial part. Once you have sorted out these issues, right, things will be a bit more smoother. But remember our maintenance, yes, that's a good point. Point. What's the undesirable effects? Really?
Problem for safety zone, because nowadays people can get hurt.
Good. One of your peers also said about having safety zones, right? So again, if you look at your workshop floor, maybe if it's human labor, you can maybe just take this area. Everybody is working, everybody is aware that this guy is doing this. I just give him a chop out, then he just take care of himself. But if you have robots, you need to ensure that they have a safety fence around them. Right? Something goes wrong, they will not damage other robots or other humans. That is the worst scenario. Yes, but that's very important as well. Right? So your workshop floor starts to increase because you have different automation. But having said that, these are the things, nothing is without its cons. There's always pros and cons. So be aware, see what makes financial sense, economic sense, in terms of getting your product quality up. Right? Then you decide. Right? Just some things for you to think about. Okay. We have talked about economic aspects, financial aspects, a bit of awareness when you have systems, what you need to consider. Now let's go down to classification of robots. When you see something, you see a robot, how do you classify it? Okay. Now first one is a remote control robot. What you see here, okay, the one on your left, right, like a humanoid, is basically a toy. But you can see it has remote control. You as the so-called the master will control the robot. When you stop the input in, he stops moving. Right? There are many systems like this. Even industrial robots. You have a teach pendant, right? Through there you input your parameters, play. It will only do that. It will not do any other thing. Right? So this is one form of robot that you have a remote control. The other one is autonomous robots. Now, autonomous robots means what? That autonomous basically means that it has the ability to make decisions. When it encounters some situation, maybe should I go left or right? Maybe he has used the sensors to get inputs, and then it decides whether I want to go left or right. Okay. Now that left or right is a very simple scenario. If you look at military, what are the targets to whack? Should I go left to avoid this, avoid that? There are a lot of other things. Even in terms of this autonomous driving cars. Have you heard about autonomous driving cars? How many of you all have heard about it? All? No. Some. If you hear from the recent news, Garden by the Bay has this autonomous driving vehicle. Right? All these are still bought from outside. Okay. internally as in like in Singapore itself, we are always trying to develop our own platforms, but we started a bit late. But that doesn't mean that we cannot catch up. So we are still building our own autonomous cars. Google has so-called successfully created one car of so-called Google autonomous cars, but they are still not on the road yet. They have gone through a lot of trials internally in very controlled environment. And when they started venturing out to do experiments on the real roads, there is always a driver behind the wheel. You just sit there, the car control. In case something happens, you have a human to stop. Okay? So, you think autonomous cars is a good idea to have? Yes, why? Why do you think it's a good idea to have autonomous cars? Okay, you can have optimized routes, right? Then you just sit in your car. Okay, I want to go here, I want to go there. That's it. It can somehow schedule with other cars. You can have a smooth journey, avoid jams, avoid erratic behavior. Suddenly you cut into this lane, so on and so forth, right? Okay. There are a lot of good reasons as well. There are a lot of bad reasons as well. Bad reason is if something happened, some accident happened, will insurance claim allow you to claim?
Interesting question.
Right? Interesting question. We have not answered that yet. That's why the cars are not on the road. Right? The insurance company will say, hey, I don't want to take the risk, man. This is on-board computer. If something happens, like that, I may not be making money by having insurance. Okay? So things to take note, and what are the things that are facing this Google or this autonomous cars from coming out so fast. That's why there are still a lot of things, a lot of policies to be talked about. Okay, this is one way of classifying robots. There is also other so-called organizations, associations who are in robotics, like from Japan, right? It's called JIRA, or Japanese Industrial Robot Association, and they have their classifications. We have also one association from France, right? So from Japan, right, they use this description, or they call it class 1 to 6. Right? They have manual handling devices, fixed sequence robots, variable sequence robots, playback, numerical control robots, intelligent robots. Right? If you look at the France one, they have manual handling devices, predetermined cycle devices, programmable devices, adaptive programmable robots. You can realize they are more or less the same, just that they are being termed differently. One call it class, one call it type, one called 6, one called 4. Okay? If you look at manual handling, they are about the same, like A and 1. Alright? Now, predetermined cycle devices. These are the fixed sequence, variable sequence, and playback. Right? So playback robot is something like you pre-program the path, you playback that path. You show the robot a path, and you just play the path. Right? Fixed sequence, maybe you are doing some kind of processors, okay, A, B, C, fixed sequence that you have. Right? Again, it's similar, it's always predetermined. Variable sequence, maybe you look at certain inputs, maybe you have a machine before this. It's telling you that, okay, right now I have 10 parts coming out per minute. Then based on that, it does the following station and that's some sequence. Maybe your number of parts starts increasing, then this thing has to become faster. For example, that's variable sequence. It's a very rough example, but then these are still predetermined cycles. Numerical control robots, basically, you can program a robot. Right? Then the process changes, you can do some changes on the fly, or before your process has been implemented, you program, let it run. But these are not still very intelligent robots. Still very fundamental, basic or decision-making capabilities. Then you have your intelligent robots or adaptive programmable. See, your robots is as good as the scenario you put them in. If you put them in a very complex environment, they don't know how to handle it. If you look at all the situations, your Roomba, for example, it needs walls around it to map and do that exercise or the cleaning. Right? It needs some conditions to it. If it doesn't have the condition, it doesn't know what to do. Same thing with robots. right? They are not like all-in-one intelligent machine. Okay, some examples of manual handling devices. Okay, manual handling means the human is there to do some form of control. Right, he's the main operator of the device. Okay? Right, things like forklift, crane. Okay, toaster wise. What is the robot? Okay, here robot. Why is the toaster inside? All of a sudden. Sorry? Correct, but you look at the heading, right? It's manual handling devices, right? So the device is very broad. It's not saying robots. Yeah. So that's why the toaster is there for your info. Right? You need to look at the classification, how they classify it. But somehow I don't know why they, when I go through the material also, because it's devices. That's why it's considered something that's it. But it looks very hard. But I want to make you all be aware to pay attention when you read this kind of standard. Read carefully. Okay. Fixed sequence, variable sequence. These are typical robots that you have. Okay. The next lecture I will go through a bit more details on the type of this kind of industrial robot. These are the typical robots that you will see in the industry. Right. Numerical control. These are things which you have very limited decision-making capabilities, but they can make some decisions. Okay, things like drones, autonomous vehicles, on land, at sea. Right? Intelligent robots are something like this. Okay, the Honda Asimov. Like humanoid can walk up the stairs, carry a tray, serve people. Just to share, this thing, this robot here, this Honda robot, if you look at the black color piece here, you know what's that? That's the battery pack. From what I understand, you take numerous hours to charge, this thing will only last you 30 minutes. Okay? So you can say that power is also a critical consideration when you are building this kind of autonomous robot. How many of y'all bought this before? The pet robot, Sony Echo. Anybody? You try to buy now? Can you buy it?
Expensive.
Still have
Still have look also.
Yeah, but they're not producing it anymore.
They're not producing, that's why it's expensive.
Yeah. See, so that was a fail. They started building it and after that they stopped. Not much market. Okay. This military robot. Okay, I want to show you this video. It's quite interesting. Okay, observe this robot carefully. I know the sound is a bit irritating, but just bear with it because this is the machine that is running on. How many of you have seen this thing before? This side? Okay, watch. Yeah, but it doesn't have any head. No head, no tail. It's just actually two. Okay, the floor is an icy floor. If you happen to go to these cold countries, it becomes something what you call black ice. Okay, why is it called black ice? Because when the snow falls, there's dirt. Then the temperature goes down, it forms like an ice layer. Again, snow falls, so it's a very black color ice, very slippery. Okay, but what they're trying to show is this, it is able to recover itself and it did not fall down. Okay, you see all these 4 bags, these are not its electronics, just to simulate some weight on the robot. Okay, they're just simulating the various terrains that you can have in the forest. You notice how you're doing the legs is just a jerk up. On a jerk up is to help it to get some momentum, plus any support you're in the mud, very sticky, Yeah. It looks like 2 humans. This is a slow motion trying to show you how is the trajectory of the leg. So you see, they never pre-program this robot, They only have a set of basic rules put into this robot, and they just play at various different terrains and let it handle itself and walk. Just do the main thing of walking. Okay? So they have a very set of very intelligent rules to help it to adapt to the environment. Okay? The other way of classifying robots is whether it's space robots, military robots, bomb disposal, rescue robots, for example. Remember in the video clip we had, they had this robot called what? Bear. It's something like this, a rescue robot plus so-called a military robot. We have educational robots. Okay, Lego Mindstorm, which you all will be playing very soon. Okay, you have medical robots, surgery, rehabilitation. Right, you can even do surgery, but this is all through for surgery. It's not an automated surgery. Thankfully, it's a master and slave concept. So the surgeon is there behind another set of manipulators or joystick, and he's doing the robotic surgery. So this can open up to tele-operated surgery. The surgeon does not need to be on site. He can be at one location, does one surgery, okay, he move on to next surgery in another place. Because everything is tele-operated via internet. Okay, so this opens up a lot of other possibilities. You don't really have to fly down to this surgeon, for example. Okay? But you need to have all this set up. You have rehabilitation, where you use robots to help maybe elderly folks, stroke patients to carry out some form of exercises. If you look at our Singapore context or even worldwide, there are a lot of people having these issues, and there's a severe shortage of therapies. They have one therapy to many patients, so they cannot give the proper attention. Just go to one patient, demonstrate a bit, go to the next one, go to the next one. The patient has to do that, do his or herself. Okay. So these are the things which are still ongoing. Underwater robots, when you're doing deep sea exploration, when you have our MH370 going down, then you have a lot of these kind of robots surveying the ocean floors. Okay. Now aerial robots. Okay, look at this particular robot. This insect robot is so small. Tip of your finger. Right. Again, experimental, but you may never know. They may go into military applications, surveillance. Right. Quadcopters. How many of you have played with quadcopters before? Anybody? Good. How was the experience? Easy to control? Right? Depends. Some of the very expensive ones have good control systems inside. So just with the press of a joystick, you can be able to compensate between certain gush of wind. We have very stable platform, for example. The cheaper ones, okay lah, very unstable. You are the controller. You see something visually, some gush of wind, then you try to stabilize yourself. Okay. A quick short video about this researcher who has very interestingly made use of this quadcopter. Not bad, huh? But you see how many robots they use? But each doing a specific task. But you see that this is a robot. Okay, social robots, you have your robotic waiters, your housekeeping, your Roombas. Okay, if you have heard, last year there was this company that was using quadcopters to serve food. Right? What's the opinion? You think it's something practical? Too noisy. If you are sitting down, something hovering around you, I don't know when the next time going to whack you behind the roadside. Right? If you notice, they never really deliver the plate to the table. You have to take it. Right? Sometimes don't be so amazed by these gimmicks. Right? They're just doing some promotion stuff. But if you really think technically, implementation wise, you'll realize that things need to be thought out a lot more than what you see. Industrial robots, warehousing, car assembly, you all are very aware of that. Okay, a quick component. What are the key components of a robot? Now, this doesn't mean that every of these components must be there. These are the major of the components. Okay? Right? So you can have generally manipulators, right, to do some manipulation tasks. You have end effectors because different tasks will have different kind of requirements. Maybe some of them need to do gripping, you need flexible arm. Maybe some of them is just so-called lifting motion. So we have different kind of grippers, different kind of part shapes, geometries, using different kind of end effectors. Maybe they don't use actuators, they use vacuums to suck up some parts, to do pick and place. There are different kind of actuators that you can have. End effectors, sorry. Actuators, the muscles, these are actually the muscles or the thing that drive the robot. If you don't have that, it doesn't work. You can have electric actuators, hydraulic, pneumatic. Right, there's a lot of other things as well as CZO, so on and so forth. So there's a whole variety of things that you can use to actuate your robot. Controller, the most important, no brain, can't do anything. Right? Even the simplest of tasks. So you can have maybe just embedded controllers as well. That is still a controller. Sensors, very important. You need to know what's going on in the surrounding. Be it light, physical sensors, maybe color sensors, temperature, so on and so forth. Okay, if you talk about the base, depends on the application. If you are looking at warehousing, yes, you need a robot maybe in the morning at location A, maybe by afternoon you should go to location B, for example, right? Whereas car assembly is different. The car is moving and the robots are just doing their parts, so they are fixed. They don't need this roving base. Okay. All right. Okay. Let's take a quick 8 minutes break. Be back by 10:30. We will start lecture 2 and then we'll just end off around 11. Okay.